Hello and welcome everyone. My name is Amanda Sturkenberg and I'm the content manager at Regenesis in Europe. Thank you for joining us for this special guest webinar today that we're hosting on behalf of Concawe. Now, for those of you who are not too familiar, Concawe is a membership organization for oil companies in Europe who carry out research and discuss environmental issues relevant to the oil industry. Our main presenters today are Marcus Hjort, Science Associate for Water, Soil and Waste at Concawe, and Richard Gill, Chair of the Soil and Groundwater Task Force at Concawe, and they'll be joined by Gareth Leonard, Managing Director of Regenesis in Europe. Before we get started, a couple of admin items first. Should you experience any sound or connectivity issues during this broadcast, then the best thing is to end your webinar session, close your browser, and then log back in again. This usually solves the majority of problems. We're also recording this webinar, and a link to the recording will be emailed out to everyone who is registered within the next couple of days, which will also allow you to share it with colleagues. Now, if you have any questions during or after the main presentation, we encourage you to post them using the webinar interface panel. I'll collect all the questions and we'll do our best to address these at the end of the webinar in a separate Q&A session, question and answer session. Also, we're trying to keep this webinar, including the Q&A, to around about an hour. And if we run out of time and we don't get to answer your question, don't worry. One of the speakers will follow up with you via email within the next couple of days. Right, that's all from me. I'll now hand you over to Marcus Hjort to get us started.
Yes, so thank you, Amanda. So I'm here today together with my colleague Richard Gill to give you an introduction to the Concawe LNAPL toolbox, which is a web-based decision support system for managing NAPL sites. So here is an outline of the presentation that will be given. So first we'll briefly talk a little bit about what Concawe is, give you some background to the toolbox. Richard will then explain a little bit about the architecture, layout, and how to access the toolbox. He will also give you a brief description of each of the tools inside the toolbox. I will then give a brief example of how you can use the toolbox to update your NAPL conceptual site model using the toolbox. And finally, Richard would give you a summary and outlook. So first, a few words about Concawe. So Concawe is a membership organization. It does environmental science for the European fuel manufacturing industry. It was established back in 1963 by a few oil companies at the time to carry out research on environmental issues relevant to the sector. And today, Concawe represents 40 member companies, which is equivalent to about 95% of the refining capacity in the European Union. And you see here all the members that we have currently, and the association is also open to any companies with any fuel manufacturing capacity in the EU. And the mission of Concawe is in 4 parts. So it's firstly to increase the understanding and the impact of the fuel manufacturing industry and the use of its product on health and environment, and is doing so through advanced scientific developments. And it's also to develop with scientific rigor what is technically feasible and cost effective in terms of achieving the European Union's goals regarding health, environment, and climate. And it's also to contribute to an informed legislative decision making and to facilitate the industry's regulatory compliance. And finally, it's also to evaluate for future scenarios the potential role and the contribution of the industry and how it's evolving in the future. And to access the work done by Concawe, you should go into our website, and here you find the Concawe report library, which also contains peer-reviewed journal articles and briefing notes that we have done. And it's a free website, accessible from anywhere, free to everybody, simple layout, and you find all the different publications grouped by subject area. And you see a QR code here on the screen, which you can follow to get to the publications on the Concawe website. We also have a YouTube channel at Concawe, and as you see here on the example, we have a video showing how to use the NAPL toolbox. So if you want so another type of introduction, how to use it, you are free to log into the Concawe YouTube channel and watch this video as well. So moving on to the background on why we decided to make this NAPL toolbox. So first of all, what is LNAPL? So it's light non-aqueous phase liquids, and we know in the industry that it's a very complex issue. We also know that there is a lot of knowledge about it, but the key knowledge is often very diffuse, so it's spread out in many different places, and it's sometimes very difficult to access and to get a complete picture. And we felt within Concawe that there was a need to better transfer this NAPL knowledge. So you see here in the cloud here some of the things that we know about it. So about NAPL. So it's a legacy of past practices. It's difficult to completely remove it. There is a strong desire for better stewardship of NAPL. There is new science, new technology that should be used, and there is a complex fate and transport behind it. And so this kind of led to the forming of this project where we wanted to make this NAPL toolbox. So we issued request for proposal back in March 2020, and inside that request for proposal there were some insights and learning. So for example, what I stated before, that there is limitations to completely remove NAPL. We know that typically NAPL is relatively stable in the subsurface. We know that it often undergoes weathering or natural source zone depletion, and we also know that the risk profile and composition of the NAPL can change with time. So that led us to the objectives of this NAPL toolbox, and the what was to provide a uniform toolbox in order to help practitioners and site managers to make better NAPL decisions at their sites. And the why was, that there's a need for a transparent and easy toolbox for the quantitative assessment of NAPL body risk management, as well as to what to do about it, so the remedial approaches. Who it was targeting was, it was the soil and groundwater consultants working mainly at Concawe membership sites, but really anyone who is dealing with an NAPL problem at the site. And the how, there was to build a transparent, flexible toolbox using science-based tools, and for it to be accessible for free and with all being in one place. And the when is that it was launched already 2 years ago, so it's been available on the web since 2022. And with that, I will give the word over to Richard to talk a little bit about the toolbox architecture, layout, and how to access it.
Thank you very much, Marcus. I'll dive straight into it. So, with regards to the architecture, the tool was built around 6 key questions that are all designed to help tease out better understanding of LNAPL issues at our site. And those 6 questions include things like how much LNAPL is present, how far will that LNAPL migrate, how long will that LNAPL persist, how will LNAPL risk change over time, will LNAPL recovery be effective, and how can one estimate natural source zone depletion. Now, for each of these questions, we've got 3 different tiers that kind of correspond to different levels of understanding. So you have your entry tier, that's tier 1, and so we wanted to provide tools here that were quick, simple graphics, for example, or tables to help orientate you very quickly on a particular question. We have this sort of tier 2, which is kind of a step up in complexity, where we introduce sort of mid-level quantitative methods and tools, which are actually hosted on the tool itself. And then lastly, we have tier 3, which is a gateway to more complex tools. So we really sort of signpost to those models that are out there, they're publicly available, that you can use to kind of dive a little bit deeper into whichever of these kind of particular LNAPL related areas you're interested in. In terms of layout and access, when you log in or when you access the tool, you see on the left-hand side the kind of home screen that will greet you, and you can see that the questions that I mentioned at the bottom of the screen, they're kind of laid out. They're laid out there, but then you can also kind of quickly access the sort of the different areas with those sort of buttons along the top to help kind of navigate, within the tool to kind of get to the relevant question you're trying to answer. Also, we have a report or a sort of a user manual that is available, which has more information on the individual tools, but also examples of how the tool can be used. In terms of how it's hosted, well, the web version is currently hosted on the Concawe servers. But if you're so inclined, you can download your own version from GitHub and host it on your own servers and access it that way. Of course, it's also important to mention that no data is ever stored permanently on the Concawe servers, and so there's a level of confidentiality and anonymity when it comes to entering site-specific information into the tool. That's not stored anywhere, and so you can use it comfortable in the knowledge that that site information isn't going anywhere. Okay, and so let's talk a little bit about the tools that are actually in the toolbox itself. But first, just to kind of give you an overview as to kind of help orientate you when you access the tool. So I mentioned about those 3 different tiers, which are your kind of access to kind of the tools within the toolbox. When you access tier 2, for example, we've got what that looks like on the right-hand side, and you can see, these are those mid-level quantitative tools, and as I mentioned, these are tools that are often hosted in the toolbox itself, and because these are slightly more involved, in often cases that these are sort of individual models that can be that are hosted on the tool. We do provide sufficient information to kind of help again orientate you around what that model actually does. So we have what the model does, how it works, as well as key assumptions and references to kind of to help you understand and make sure that you're familiar with not only the input of what you're putting into the model, but also what the output is. It can be used for as well. So just to focus on the first tool first of all. Now, with regards to each of the 3 tiers, I won't go into detail on each of the tiers for each of the different tools. I'll just highlight 1 or 2 as we go through. And so for the first tool, this is really trying to answer the question, how much LNAPL is present on a particular site. For the tier 1 sort of entry level understanding, we try and relate some information about LNAPL specific volume. And this is all about relaying the importance of soil properties and the relationship between the amount of LNAPL in the formation and the thickness of LNAPL that is observed in a groundwater well. And now this table shows the specific volume for 4 different soil types, depending on the LNAPL thickness observed in a well, to give a guide as to the actual amount of LNAPL that might be found in the formation. Now moving on to tier 2, so this is on the right-hand side, bottom right-hand side of the screen. This is a tool that calculates several key LNAPL variables, including specific volume again, recoverable volume, and transmissivity at multiple locations for multiple layers of differing soil types. So here you have an opportunity to enter more site-specific information, and these values are then used to calculate the total subsurface LNAPL volume based on LNAPL gradients that can be entered by the user, as well as estimated LNAPL velocities can also be calculated. The distribution of the calculated values is depicted graphically, so there is a sort of map overlay so that you can use to kind of help visualize where the LNAPL is on your site, and use that to kind of get an idea for the amount of LNAPL present. Now, this is all based on the LNAPL distribution and recovery model from the American Petroleum Institute. And indeed, when we talk about when you were to access the sort of tier 3 gateway to more complex models, this is the model that we point you towards. In terms of the second tool, this is all about trying to answer the question, how far will the LNAPL migrate? Now, just focusing on the tier 2 models that we have in place here, we have two different migration models that are available to you. So we have the MALA migration model, and we have a specifically developed model for the toolbox. This is the Kirkman LNAPL additional migration tool that both of them also integrate this sort of natural source and depletion component. So first of all, the MALA migration model, so we include that on the left-hand side, the bottom left-hand side of the screen, so it's a screenshot there. This illustrates the natural losses of LNAPL, for example, through natural source zone depletion, and how that can play an important role in governing the overall extent of the LNAPL body at the site. So the model calculates the overall length of a contiguous LNAPL body, given a certain inflow rate of LNAPL, an NSCD rate, and over a certain time period. So it kind of gives you a kind of an overview there. And then we have the Kirkman migration model. So that's on the right-hand side. So this tool calculates the additional distance that the leading edge of an existing LNAPL body is expected to migrate until it eventually stabilizes in the presence of natural source zone depletion. So it kind of really gives you, again, an idea as to how far it might migrate under those certain circumstances. For the third tool, we look here at trying to answer the question, how long will the LNAPL persist? Now here I just want to talk a little bit about the sort of tier 1 tools that we have here. So what we present is kind of highlighting the existing evidence that demonstrate the role of natural attenuation processes to reduce both LNAPL and also key risk-driving compounds over time. And so the graph that we have here is information from the GeoTracker database that is used to determine, how LNAPL thickness changes over time, but also, as it's shown here, constituents such as benzene, and we also present things like half-lives from, statistically significant number of sites. For example, here this GeoTracker information is leveraging the information from over 1,000 sites, so it really gives you a robust foundation to kind of make conclusions or use half-lives and things like that through in risk assessments and such. So that's your kind of tier 1 level entry there for that particular tool. Moving on to the fourth tool in the toolbox. So this is all about trying to answer the question, how long will the LNAPL risk how will LNAPL risk change over time? And again, so looking at this sort of the tier 2 model here, we have a model that calculates the theoretical concentration of dissolved hydrocarbons in groundwater down gradient to an LNAPL source, and how that those concentrations change over time due to dissolution processes. So this is looking at the groundwater immediately down gradient from your source zone, and here you can enter information about, well, not only the kind of the groundwater conditions at the site, the hydrodynamic conditions at the site, but then also the LNAPL constituents that you have in your LNAPL body. And you can see there the kind of output you can anticipate from the tool, and how based on the kind of flushing of those constituents over time, what the concentrations will look like down gradient. For the fifth tool, this is all about answering the question, how will LNAPL recovery be effective? And I wanted to highlight here some of the more complex tools and models that we point to under tier 3. And you can see here that we're not just providing a hyperlink, we're providing a little bit more, again, orientation around these particular tools, which can, frankly, be quite complex to kind of get to grips with in the first instance. And so we have explainer videos and as well as that sort of more detailed information about how to use the tools and access them available under that tier 3. So lots to explore there, and certainly a good foundation for getting to grips with these more complex tools, should your conceptual site model need it, of course. And then lastly, we have this we have the sixth tool, and this is all about estimating natural source zone depletion. And I wanted to talk a little bit about what we've got under tier 2 here. So we have two different kind of tools under this. Firstly, we have this NSCD rate converter, which is all about surmounting the variation in rate units used in the literature, and again can be very helpful when trying to translate gallons per acre per year into something more like liters per hectare per year, for example. Then we also have an NSE temperature enhancement calculator. So this is all about trying to understand how hydrocarbon degradation can be enhanced with increases in temperature, and this model uses the Arrhenius law to estimate the potential NSED rate enhancement with any externally created temperature increase up to about 45 degrees Celsius. So again, very helpful to kind of understand, okay, well, how might those rate changes if I were to tweak conditions at the site. And that's an overview of all the tools. Now, my colleague Marcus will walk us through how those tools can be applied to better understand our conceptual site models.
Yes, so thank you, Richard. So with this example, I will briefly go through 8 steps showing how the toolbox can be used. It's all used on a theoretical example, so there's not a real case. And a more complete description of the different steps that I will be presenting is present in the toolbox manual that can be accessed on the Concawe website or inside the toolbox itself. So first, the first 2 steps. So here, the site owners is using the toolbox to develop a more accurate estimate of the NAPL specific volume, and in order to get a more accurate estimate of the total NAPL volume that is present in the subsurface. So by using this, a new volume is estimated, which is in this case lower than the original estimate that was previously in the conceptual site model of the site, since the former one was then based on an inaccurate understanding and inaccurate assumptions that were that was the basis of the understanding at the time. So this is a way to then get a better update or better estimate of the total NAPL volume in the subsurface. And also while looking at the step 1, so then moving to step 2, it indicates that a more detailed information would be beneficial to even better understand the NAPL volume at the site. So here it's using then the tier 2 of the first tool, so how much NAPL is present. So site data is compiled and then entered into the input data spreadsheet of the model in the tier 2, and this gives even more refined estimate of the total NAPL present in the subsurface. And it also gives another piece of information. It shows how much of the NAPL that is potentially mobile, and also the amount of the NAPL that is permanently trapped as residual NAPL in the subsurface. So with this, the model in the tier 2 of tool 1 is further developed to map the NAPL transmissivity that is then based on the site-specific NAPL properties. With this map, as well as with the guidance done by the US Interstate Technology and Regulatory Council, shows that only one well out of all the NAPL skimming wells exceeds a threshold, which then says when hydraulic recovery of NAPL is efficient, sustainable, and cost-effective. So when these new calculations are formed and consulting this guidance, it's indicating that all but one of the skimming wells are not providing much environmental benefit. And as well as using the tool 1, also the tool 5 on will NAPL recovery be efficient, this shows similar results. So that's both of those are increasing the confidence that the NAPL recovery should be should be terminated at all but at one of the existing NAPL skimmer wells. And then moving on, understanding a little bit more how far the NAPL will migrate, reading in the tier 1 of the tool 2, so how far NAPL will migrate, that indicates that natural source zone depletion is a key factor in stopping the continued migration of the NAPL bodies, and the tool 2 of tier 2 on how far NAPL will migrate informs that NAPL models usually that does not consider natural source zone depletion is likely to overestimate the NAPL migration. So in this example, then site consultants and site owners determined that more information about the NSCD would be key to update the NAPL CSM. But none of them have a really strong background in this area, so therefore they also consult the tiers 1 to 3 in the tool 6. How does one estimate natural source zone depletion? So based on that and consulting the tier 1, they show that where it's shown that almost all NAPL bodies are naturally attenuating at the rate from 10 to 100 times the rate assumed in the former conceptual site model of the site. So therefore, site consultants begin to evaluate if the literature values provided in the toolbox are sufficient to update it, or if they need to go into more site-specific measurements of the site. And then going to step 6 of this example. While discussing how to get better natural source zone depletion rates at the site, they're using the mid-range rates that are provided in the tool. So and they insert these in the model of tier 2 of the tool on how far NAPL will migrate, and they insert this in the Kirkman additional NAPL migration model. And it shows then that the existing NAPL body is not likely to expand to any significant degree, even if the NAPL skimming wells were to be shut down. So this provides additional support that the skimmer wells have done their job and can be then retired at the site. And then they look at this theoretical example. They also look on the potential longevity of the NAPL to update the conceptual site model. So after reviewing the tier 1 of 2, 3 on how long will the NAPL persist, they apply the model that is in tier 2 by entering the new NAPL volume estimates that they got from the earlier steps from the other parts of the tool. They also input the area of the NAPL body, and they use these mid-range NSCD rates. And from this, they obtain 2 different NAPL volume versus time graphs, and where one of them assumes a constant NSCD rate and suggests that all the NAPL will be removed by the year 2030, and whereas the second graph includes declining NSCD rates and then suggests that 90% of the NAPL will of the present NAPL will be gone by the year 2050. So this gives 2 different, quite a long range of the estimates, and it informs the new conceptual site model that these estimates have a significant uncertainty, but both of them shows that even the NAPL is being removed over time at the site. And then because of this uncertainty in the longevity estimates, site consultants and site owners become then interested in the estimates, in these estimates, and how this could change the groundwater exposure pathway associated with the NAPL, how that will change over time. and currently there is no ongoing risk at the site as no exposure pathways were completed. So then they run the model 2, the model in the tier 2 of tool 4, how will NAPL risk change over time? And that gives them a forecast of the benzene concentration over time. And with this forecast, they then later run a more sophisticated NAPL model called the REM fuel, which is then described in the tier 3. So this is one of the more complex tools, which is then part of the tool 4, how will NAPL risk change over time. And based on this information, based on the description of the REM fuel in the toolbox and the information provided in the videos that are linked to in this tier 3, they run the model, and the modeling efforts show that the risk associated with the hypothetical groundwater exposure pathways over time is reducing faster than the likely NAPL removal rate. So that's a good sign in order to update their CSM. So then overall, how this in this hypothetical example, how the toolbox have helped the site owners and consultants to update the former incorrect NAPL CSM. It has then been updated and strengthened the case for firstly the retiring most of the old inefficient NAPL skimming wells. So the data that is put out from the toolbox shows that there is no gain on keeping these skimming wells operative, so they can all but one actually be retired, and that saves both cost and time for the people working at the site. There is a better understanding that further significant NAPL migration is unlikely, and also the outputs of the toolbox shows that the benzene concentration are expected to go down over time. It has also helped the site owners and consultants to go into using natural source zone depletion as the NAPL management technology in the future. So probably a bit more research and development is needed there, how to include this in the site management going forward. And it's also shown with the toolbox that there is a need for the continuing long-term groundwater monitoring to ensure that the long-term removal of the NAPL body by this natural source on depletion is on track. So it will retire most of the old inefficient NAPL skimming wells, but there is a need to then maybe understand the natural source on depletion a bit better, and they need to still continue to monitor the groundwater at the site. But overall, the conceptual site model can be well updated, and understanding of what is going on with the NAPL body in the subsurface of the site is greatly improved overall. So with this, I will hand the word back to Richard to give a summary and outlook.
Thank you very much, Marcus. Yes, and in summary, it's a great tool. It touches on the 6 key questions that can really help frame the LNAPL components of a conceptual site model, which we've gone over. It presents it in a logical, stepwise fashion with graphics, explainers, and calculators, and it also includes links to the next step. Links to more complex tools. So I encourage you to go ahead and try it. It's available. It's available for access in the website address below. You can download it, as I mentioned earlier, via GitHub, or indeed using your favorite search engine. You can search for the Concawe LNAPL toolbox, and that should take you straight to it. We also have a QR code coming up, so you'll be able to access it that way too. So that just leaves me with a big thank you to the members of the Concawe Water, Soil and Waste Management Group, and the folks at the Soil and Groundwater Special Task Force who helped initiate the project and got it running. I'd like to say a big thank you to the beta testers from the Concawe company, and of course our friends at GSI Environmental who put the tool together. And Brian Strasert and Hannah Podzorski were both instrumental in from GSI, formerly from GSI, at pushing this project forward. So a big thank you to them. And of course, thank yous wouldn't be complete without a big thank you to you for your attention. Thank you very much.
Right. Thank you very much, Richard and Marcus. That was really interesting. My name's Gareth Leonard. I'm the Managing Director of Regenesis. I thought that tool is really good at helping people come up with intelligent designs for sites, for petroleum hydrocarbon sites, in terms of whether you are going to do active remediation or whether you can look at natural source zone depletion. Where I wanted to go with this, just to finish off for the next 10 minutes or so, is on sites where potentially there is a residual down gradient risk in the dissolve phase, and give you an option as to what you can potentially do with that. So if we stick with the concept, if I can get my slides to work, if we can stick with oil refineries, you might have a leak, a spill on the oil refinery itself, and that then has the potential to create a series of liabilities that then need to be assessed. So you've got in red here, you've got the on-site liability. So that is the contamination on the site itself, the soil contamination, the LNAPL contamination on the site, which may not be moving very far, certainly in terms of the soil isn't, but the LNAPL may not be moving very far. And that may be something that then you can just monitor over time, because the refinery is going to stay there for many years. So this on-site liability doesn't necessarily need addressing straight away. You may have an environmental liability where dissolve phase contamination is moving away from the source zone and it is getting into an important aquifer. So it might be that the aquifer itself needs some form of treatment, so that would need to be part of the assessment. You then have the possibility that your plume is moving over a site boundary. So you have a legal liability there, that there might be an offsite liability as it crosses your boundary into a neighboring property. And so works may need to be done there, active remediation may need to be done there. And obviously beyond your site boundary, there may be receptors. So surface water, there may be potable drinking water, things like that. You can also have the scenario that on-site or off-site, you have a human health liability as well. So there might be residential properties, might be offices on the site, etc., where vapors may be getting in, or again, potable drinking water, something like that. So what you can do is look at how to treat this contamination in the most intelligent way. So you may be doing active source treatment, you may not need to do that. So it might be a matter of monitoring that and make sure that you're not getting migration of that source zone. But what you do need to do is, while you're allowing the plume to attenuate over time, you're protecting those down gradient receptors, removing your offsite liability, etc. So one way of doing that is installing a permeable reactive barrier. And I want to go into an injectable permeable reactive barrier today. A permeable reactive barrier is one that allows groundwater to flow through it, but it treats the contamination. So you get contaminated water moving into it and clean water coming out of it on the other side. So the product I'm going to talk about over the next 10 minutes or so is Petrofix. It is made of a colloidal activated carbon. So what we've done is we've taken activated carbon and we've ground that down to 1 to 2 micron. So that's about the size of a bacterium. It's about the size of a width of a red blood cell. So these are small. You know, the activated carbon that you may be used to is granular activated carbon for treating water, or even in your kitchen for drinking water, etc. That might be about 1,000 micron. Powdered activated carbon, maybe anywhere between 20 and 200 micron. This is very small, 1 to 2 micron. We've then suspended that in water with dispersion agents. And the reason we've done this is to make it easy to inject. So it comes as a concentrate on site, you dilute it, you pump it into the flux zones under low pressure, and it coats the subsurface. As it moves through the subsurface, it coats the subsurface, and it creates a subsurface filter for removing petroleum hydrocarbons out of the ground. Within there are nutrients as well, which drives the biological degradation. So it's doing sorption and bio. So I'll go into that a little bit further. There's a number of steps in the remediation process that I've split up here. So the first thing is sorption. So this is what the product looks like. It's a liquid, flows into the ground. You're using direct push generally, but you can inject it into wells, or you can pour it into the base of excavations, etc. You're not fracturing it in. You're flowing it in so that it is going along the flux zones through which the contamination is moving. So if you look at these scanning electron microscope pictures, you see a clean sand on the left. We then move this colloidal activated carbon through that material. We've zoomed in a bit more on the right there, and you can see individual particles of activated carbon coating the aquifer itself. So we're actually engineering the aquifer from having what may be a very low fraction of organic carbon to an incredibly high fraction of organic carbon, because we're not just adding carbon, we're adding activated carbon. So it's much more sorptive than natural carbon. So that massively increases the retardation factor of the contamination moving through the groundwater. So it's perfect for barrier treatment. So here's just an animation. We're putting the product into a permeable zone in between two less permeable zones. It removes the contamination from the groundwater and it sorbs to the material itself. Any further influx from up gradient is then sorbed. And then what you have is contamination that is diffused into the immobile porosity, maybe silts and clays, that back diffuses out, and that is also sorbed by the product itself. So you're not just treating what's in the flux zone, you're treating what's in the entire aquifer. So this is just a quick example of showing how it flows through flux zones. We've got two columns of silty sand. On the left, we've got the colloidal activated carbon. On the right, we've got powdered activated carbon. We're just pouring water onto the top of it to drive that through under gravity. Now, the powdered activated carbon technically should be able to move through this. It's about 20 micron, but what it does is it sticks back together, it flocculates, coagulates, so that you get effective particle size of about 1,000 microns, so it just doesn't move. Whereas you see with the Petrofix, it flows through the subsurface and it is coating the subsurface as it goes. So it's not being washed out, it is painting that subsurface as it goes. Okay, so the next step, once it's stuck to the aquifer, once it's sorbed the contamination, is it then biologically degrades that contamination. It's anaerobic oxidation, which is matching the anaerobic conditions within the subsurface. So if you're doing a site investigation of petroleum hydrocarbons, you may well put a trial pit into the center of the plume. Now, you've spilt the petroleum hydrocarbon, it's a clear liquid. It might be in sand, which is like a buff colored geology. You put your excavator into the ground, have a look at it, the ground is black. Now that's telling you that it's anaerobic. You've got these iron sulfides being laid down because the microbial growth in there has removed the oxygen, and you've got increasingly anaerobic conditions in there. So what we do with this is we push in the same direction. We add sulfates and we add nitrates so that we create a consortia of microbes that are not competing with each other over the nutrients, but they are working together on degrading that contamination. So we create a large effective biomass, it kickstarts the biological degradation, and then that is maintained by the natural sulfates and nitrates in the subsurface. So here we can see we inject the sulfate nitrate concentrations. They don't last forever, they'll last for a few months. But what happens is we build the biomass, and then that biomass continues to survive, it continues to feed on the sulfates and nitrates naturally occurring in the subsurface. And you can see that by doing quant-array of the microbes in the subsurface, and you can see that they continue to grow beyond the period in which the sulfates and nitrates we've added are there. They've been used up, but the microbes continue to thrive, degrading that contamination. So what does that mean? That biological degradation regenerates the sorption sites of the Petrofix. So we've coated the aquifer in colloidal activated carbon. That sorbs the contamination. We then promote the biological degradation, the growth of microbes. These are benthic, so they grow on the biomatrix, on the activated carbon. They degrade that contamination, which then frees up the sorption sites. And that means that further flux coming in will then stick to the activated carbon. And this is a repeating process by which we sorb the contamination, we degrade the contamination. That allows us to free up the sorption sites and sorb more contamination coming in, degrade that, etc. So this constantly cleans itself in the subsurface as a filter. So it's applied very simply. It comes as a concentrate. You add it to water just to reduce the viscosity slightly. So the viscosity upon injection is similar to that of water. You want to get a decent volume in there to get interlocking radius of influence. You then use direct push, so you'll putting certain doses in at certain levels to target the flux zones. You then move the rig to the next location, inject again, and you're looking to get interlocking radii of influence. So you want to get an overlap of something like 30 to 50% of your injection radius to ensure that you are then treating the whole zone. And you might be doing this as a grid, or in the cases I'm talking about today, you're doing it as a permeable reactive barrier. So permeable reactive barriers, this is viewed from above. You want to have interlocking radii of influence so that you're not having contamination move through those gaps. That spacing is going to be determined on how fast the groundwater flow is. So you might need to tighten that spacing up so that you're targeting targeting all the contamination coming through. The other thing you might want to do is, if you have a lot of flux coming in, you might put in 2 rows, and that second row you'll offset by half, which is called a herringbone pattern, so that you can deal with the flux, which is the amount of the speed of the groundwater flow and the amount of the contamination coming through. And that flux determines the spacing, determines the dose that we put in. So this is what direct push looks like. This is injection of a different product actually, but there's direct push injection in a site in Finland. And what I want to discuss on this site is we're replacing permeable reactive barriers, or we're replacing slurry walls, we're replacing funnel and gates. So that generally involves large equipment, that involves putting piling mats down, things like that. Now with this, we've got a very small footprint. We're not on site for very long. We just inject into the ground, and that's it. The carbon will essentially last forever, and the barrier will degrade that contamination as long as that contamination is coming in. So as it depletes, eventually your site is clean, and what it's doing is it's preventing impact to any down gradient receptors in the meantime. So there's no piling mats, there's no excavation, no off-site disposal. You're not getting in the way of a construction program. We can get in and out, and there's no impact on the developable footprint. So what does that mean? It means if you're putting in one of these big slurry walls, you have to position your buildings to take into account that you're having a geotechnical effect on the ground. This has no geotechnical effect on the ground, so you can build on top of these barriers. So just to finish on a quick case study, this is a site in Italy. There was a petroleum hydrocarbon tanks in the ground on this industrial site. They were removed and cleaned up. They then built the building before they had permission to deal with the plume. So what they did is, it's part of the building, they put in injection wells into the service corridors in the basement, the subsurface parking garage, basically, with the idea that we could deal with the plume when they got permission from the regulators to do so. So it's 14 wells, 4-meter spacing, is quite wide spacing on here. The treatment layer is quite narrow, just 1.5 meters. So we're putting in about 2,000 liters per point. So put that in nice and gently because it's in a narrow band. But what we want to do is it's a good amount, good volume. We're trying to get that interlocking radius of influence over that 4 meters. This was applied October 2021. Took about 5 days on site. Quite an interesting one to do. There's people in the building, coming and going, working. So the other thing, it's a really nice new building. this material is black. We don't want to make a mess on this building. So we doing the mixing outside, very straightforward. Just add water to it, mix it up, and then we'd pump it down a pipe that would go down through the air vents, down into the basement, down into the service corridors, and we would clip on with a packer into the injection wells and inject. And these are the results. So the graph on the left is the results within the barrier itself. So very high concentrations down to zero. Now what you're seeing is sorption, but then biological degradation is going on that sorbed material. So you see the reduction is dramatic. That's the sorption. Bio will then continue and degrade that contamination. New contamination coming in is sorbed and degraded. And you can see that there's a little bit of a lag, but then down gradient, you see these lower concentrations drop to non-detect. And then after a year, the site was closed out. So utilities for hydrocarbon plume treatment, it can be used in the source area, it can be used in the middle of the plume, or to protect down gradient at the distal end. You can apply as a barrier in a source, a grid in a source, a barrier as I talked about today. It can be used on refineries, petrol filling stations, industrial sites. It's used on domestic oil spills, things like that. Very easy to use, very good distribution, creates a subsurface filter, which gives you a rapid reduction, but then it lasts a long time. And these are the types of results you get. So I hope that was interesting. I am going to put up Concawe's final slide, and then I'll ask Amanda to come in and see if we have had any questions.
Thank you for that, Gareth. Yes, well, thank you first of all to Marcus and Richard as well for your great explanation of the toolkit. That was really good. We have some questions that have come in already. If any of you think of any others as we go through answering these, do keep posting them, and I will do my best to pick them up as we go along and fit them in. So one of the first questions that came, or not the first, actually one of the last ones, it may be someone who's missed the beginning, a question about cost. Is there a cost to using the toolbox? I don't know which of you would like to answer that.
Yes, so I will take this, Marcus. So no, there is no cost in using it. It's freely available online on the website, or also freely available to download the source code for installing it on a computer that is not connected to the internet. So it's no cost at all.
That's brilliant. Thank you. Right, let's have a look. Another question then, are there any special activities that need to be added to a site investigation in order to accurately model using the tools that you presented in this toolbox?
I can take this one. So Richard here. Yeah, no, I would say no. The inputs to the LNAPL toolbox all kind of stem from the usual suite of site investigation tools available to the consultant community. Really to kind of get the most out of the toolbox. It may be that you need to consider sort of further site investigation, but only as a mechanism to better understand your conceptual site model, and then subsequently the inputs that you would then put into the toolbox. So it's really all kind of stuff that you should have access to, but it's really kind of there to facilitate your understanding and the development of your understanding around the conceptual site model.
Brilliant. Okay, thank you. Yeah, one of the questions here is how many sites have been modeled using the toolbox so far?
Yeah, so I can take this one. So since we're not storing any data from the toolbox and how it's being used, we don't have any hard numbers on that actually. But I'm aware from personal communication that at least 2 of our member companies are using the toolbox. At least 7 consultant companies, both big and small ones, are using it, and as well as one organization that deals with soil and groundwater remediation. They contacted me last week asking to use part of the output of the toolbox in one of their publications and reports, and that was of course no problem to use. So while don't we have any hard numbers, we know that there is usage of the tool, but yeah, no detailed statistics.
Okay, brilliant, thank you. Here's one for you, Gareth. Can Petrifix deal with LNAPL?
Well, the short answer is no to that one. Essentially, LNAPL is going to blind the colloidal activated carbon. It's essentially it's too much mass for it. So what we're aiming at doing is dealing with the dissolved phase plume. Be aware though, Petrifix is a sledgehammer of a tool in your toolkit. It can deal with very, very high concentrations, and it can take you to very low concentrations. So you can go right up into the source area with this. But this is a good example of where using the toolbox to work out what your LNAPL is doing, so you can position a barrier, it is a good thing. But an example would be that if you are on, say, a petrol filling station and you've got fuel on the side, you would put this in at the edge of the site immediately to prevent your offsite liability. And then once you've done some source treatment, there might be some excavation, there might be some skimming, etc. You might then go into that source area and deal with the residual contamination by applying the Petrifix to reduce that residual mass. But yeah, you try to avoid applying it into areas where there is actual NAPL in there.
Okay, that's great, thank you. I'm just looking at the questions here. There's some more that have come in, but I think we have time for, well, let's do two more. Right, I've got one here. What effect does temperature have on source zone depletion?
I can I can do that one. So really, there's effectively a positive correlation between the sort of temperature increase and the rate of biodegradation. And this is described by the Arrhenius law that says that the rate of degradation increases with a doubling of the temperature, right? So as the temperature increases, then the rate increases as well. But mind you, of course, this is up to a certain point. So approximately about 40 degrees, you can increase the temperature up to before microbial populations start to decline. Just as a kind of a rule of thumb, anaerobic digesters operate at about 35 to 38 degrees Celsius. So that kind of gives you an idea as to where that optimum can sit.
Okay, lovely, thank you. Right, this is the final one then. How have users responded so far to the modelling? Is there a difference in response from different countries, etc.?
So maybe this might be one for me and you, Marcus. I think just at a high level, I think that the feedback has been positive. Fundamentally, the tools based on the latest science and our latest understanding of LNAPL, and it's intended to help practitioners, as we've said, develop the conceptual site models and thereby reach more informed conclusions of what their site management approach should be. But that should always be done in view to local regulations and what is permitted to do for contaminated land. I'm not sure, Marcus, you mentioned you'd had sort of feedback from different individuals. Has that ranged in geography at all?
Yes, I think so. I think it's been mostly, well, the range has been mostly in Europe, I would say, so far. But it's a tool that can be used worldwide, and there's no kind of regional restriction or that is better used in one area over another. But it's really about concentrating the knowledge all in one place and get the knowledge out there and to practitioners and site owners to better understand their site and with the aim, of course, to help in discussion with regulators and with the public, of course, but to increase the knowledge. That's the main aim.
That's fantastic. Well, that's exactly, I think, what this toolbox is doing. Thank you both so much for your presentation. Just to say, any outstanding questions will be answered by Marcus, Richard, or Gareth within the next couple of days via email. Just some final bits of information. In the next hour, you'll receive all an email with your attendance certificate already attached. So if you need this for CPD points or other ways of tracking your ongoing learning, then look out for the email from GoTo. Inside this email, there's also a link to a short feedback survey. And as always, I'm encouraging you to complete this. It's useful for the speakers to get your feedback on the delivery and content of the webinar. And it also helps us plan future topics and our next guest speakers. So thank you once again, Marcus, Richard, and Gareth. And thank you for all of you for joining us, for spending your time with us, and have a great rest of your day. Thank you. Bye-bye.